Hello. So today we will have our first lecture about algorithm design and analysis. So I will start with a simple algorithm that the insertion sort that everybody should know. Actually, you should learn about insertion sort in at least CMPS 280, sometimes earlier. But for this class, we will pay more attention to how to design it, how to analyze it. In other words, how to know that insertion sort is not a good algorithm. Okay, so let me share with you some slides about the purpose of this lecture. So what is this course about? And as you can see on the shared document, here we want to basically learn how to design an algorithm, but not any algorithm or any program, but a correct one, okay? And the one that always terminates, meaning that it will not hang, or in other words, whenever you provide an input, the algorithm, the program will finish working after a certain amount of time, of course, depending on the size of the input. Okay, and for this class, we particularly interested in analyzing the performance of the program. Okay? In other words, we want to know whether or not the program we just finished writing is a good one, or if it's not good, then how can we improve it? So we will try to have two different tasks here for this insertion sort algorithm. The first one is how to analyze the algorithm, meaning that we want to predict how long will the program take if we give an input for the program. Okay? You may ask, how do we predict? Okay? So we need to analyze the algorithm and have some calculation to see, say, how fast the algorithm can be. Okay? And the second thing is about design. How can we design an algorithm that minimize the cost? Okay? Minimize the cost here means that we minimize the running time and we minimize the resources needed for the program. So in other words, there are two things we want to minimize. The first one is the running time, meaning how fast the algorithm can be. And the second thing is about the resources. For example, how megabyte of memory space of the RAM the program requires. Okay? You can see that nowadays, most of the programs will require a lot of memory space, like uh, Microsoft Word or Microsoft Excel. It may require at least 4 gigabytes of RAM, right? But long times ago, 30, 40 years ago, a program that can do the same thing can require just only 200 megabytes of RAM or 128 megabytes of RAM. So, of course, someone will try to use more memory in order to speed up the program. And in this class, we will also analyze it to see if you want to use too much of the memory, that would be a problem for the users, right? So we cannot afford to buy computers with 100 gigabyte of RAM nowadays. It's too expensive, right? So that's why we want to design the program that will, number one, fast, and number two, requires minimal resources of say memory or displays, etc. Okay. Now you may want to ask, when we write a program, we analyze it first or we design it first. Okay, so here I show two things, analysis and design. But which one should we perform first? Say insertion sort, should we design the insertion sort first, or should we analyze the insertion sort first? So basically, what we will do is as follows. Okay. Starting with insertion sort, what we will do is to design an algorithm, and then we will analyze it to see if it's good. Okay. Yes, then we are done. No, we have to go back and redesign. And after we redesign, analyze it again. If it's still not good, we go back, redesign it multiple times, and until we are satisfied with the algorithm. Okay, so in other words, analyze and design will have to be done in a circular approach, something like this. Okay, so now we will try to have the sorting algorithm. Okay, the sorting algorithm means that we are given an array or a sequence of numbers, and we have to design the program so that it will sort the input sequence, so we can have a sorted sequence of numbers. Okay, so let's start with one simple example. As usual, in order to design a program, we always start with a simple example that is not too big, that is not too small, so we can know how the steps, or how many steps do we need to take, or how the algorithm should work. And based upon the results of a simple program on a simple input, we will try to design an algorithm for a generic input. So first, we have a simple example here. We have the list of number 8, 2, 4, 9, 3, 6. Okay. All right. So now I will turn off the share document. Okay, so we can work on the whiteboard. Yeah. So now the insertion sort works by first split the input sequence into two parts. Okay. The sorted part has one element, that is the one on the leftmost position, and the rest will be unsorted. So this one is the unsorted. Also, for this particular design, I will use the indexes for the number from 1 instead of 0. Okay? The reason for that is number one, many programming languages has the index start from 1, like Pascal, like Maple. And the second reason is that when we have the index from 1 to 6, it's easier for us to analyze the formula for the cost or for the performance of the algorithm. You will see later on when I try to count the number of steps for analyzing the performance of an algorithm. If we have the index from 1, it's easier. Okay? In fact, it's a lot easier instead of indexing from 0. Okay, but it's just a minor thing. Okay? We count from 1 instead of counting from 0. Okay, so now how does it work? The insertion sort algorithm that I asked you to remind yourself before coming to the class today is that starting with the unsorted path here, we will try to insert the first element of the unsorted path into the sorted path. Okay, how can we insert this? So first, we will compare the value of the sorted path. If it's bigger, we move it to the right one position, right? So that said, we will try to have a variable to keep track of where we are dealing with the elements of the unsorted path. Okay? So I will choose J here is first started with 2, right? And when we compare, if it's bigger, we have to move or shift it to the right. And we have to keep track of the value here, otherwise it will be overwritten by the sorted elements, right? So in other words, we will try to have another variable we call key, that is the value of this cell or this position, right? So when we insert the elements, we will try to see so how many elements we have in the sorted path. If it's bigger, we shift to the right one position. Now we have 8 here. And no more elements in the sorted path, so we will store 2 to the position of the 8 before, right? And the rest are still the same. But now the sorted path will have one more element. So after we insert this one, we have 2 sorted elements, and the unsorted path will be reduced by 1 as well. So similarly, we will try to insert 4 into this sorted path by storing here. Okay, J now will be 3, right? J now will be 3. And now the key will be 8, 3, right? So we insert this by comparing it with the value of the key. It's bigger, so we move it to the right. Okay. Go to the next. It's smaller, so we don't do anything. So we will write 4 to the place where we just moved it out. 2, and now we have 9, 3, 6. And now the sorted path, we have 3 elements. The unsorted path has 3, right? Continuously, we insert this one in. It's bigger than every element on the left-hand side. So we have it the same, except reducing the size of the sorted path. And now when we insert this one in, we will move 9, and now, okay, 8, 4, 3, and 2, right? 6 is still the same, right? And the last step is inserting this one by scanning the sorted part from right to left. Is bigger than 6, then we move 9. 8 still bigger than 6, okay, move 8. 4 is smaller, so we write 6 here. And now we have 4, 3, 2. And now the sorted part has all elements, and the unsorted part has no element or is empty. Okay. Hence, the algorithm stop here, right? Because we already sort the input array. So that is the idea of the insertion sort. Nothing new, right? Everybody should know about this. So now we will try to design an algorithm that follow the steps we just did here for this simple example. Okay. So now the steps we have for this is as follow. So the steps is something like, okay, first, the sorted part has one element, the unsorted part has n minus one element, right? And why the unsorted part is not empty? Okay, what will we do? We will insert the first element of the unsorted part here, or in this case here, into the sorted part, right? So here's what we will do, right? And then after we insert that, we decrease the size of the unsorted part and at the same time increase the size of the sorted part. All right, so that is a rough design of the algorithm following the steps we did here. So once we have the design, we want to convert the design into a program, or more precisely a pseudocode, right? So before we can convert a design into a pseudocode, we need to look at what we have here and try to see whether or not we need to make some steps clearer. So in this situation, we have the step, insert the first element of the unsorted part into the sorted part. How? Right? So how to insert this one? So from here, we can say that we need to make it a little bit clearer. So how clear should we do? Insert this one by scan the sorted part from right to left. While scanning, we compare the values of the sorted elements. If it's bigger, we move to the right one position. Okay? So we have to scan every element here on the left-hand side. In other words, of the sorted part. So that said, we make it clearer by adding the red sentences here. Okay? Scan the sorted. If the element is greater than the inserting elements, then we move it to the right. Okay, so we are ready to convert this design into a program. Okay, I suggest that at this point, you don't watch the video or you don't look at what I will do on the screen or on the whiteboard, but just try to do it by yourself. Okay? After we have the algorithm design, as I showed you on the share screen, convert that into a program, a pseudocode. Okay. All right. Now we will try to do it here on the whiteboard. Here. So what we will do is as follow. We will try to convert the design into the pseudocode. So insert, sort. The input is an array that has n elements, right? Okay, so why the unsorted part is not empty? As we see here, we can choose a variable or an index that goes from 2 to the end, right? So that said, we have y, the unsorted is not empty, right? So we do that by a for loop for j from 2 to n, okay? From 2 to n, we need to keep track of the values of the first element of the unsorted part, right? And then after that, we scan, okay? So that said, we would have key is assigned with a j, right? And after that, we insert this one into here. So we need to find out where we start scanning the value. That is what we start. We can have a variable I here, right? J minus 1 is where we start scanning the values in the sorted part. And then y, okay, I is greater than 0 because we only scan the values from the the last element of the sorted to the first one, meaning it cannot go beyond the index 1. And okay, AI is greater than the key, meaning if it's greater than, we move to the right one position, right? So this one is what we call scan. Okay? What we will do is that if it's on the sorted part and if the value is greater than the key, we shift one position, meaning I plus 1 is assigned with AI, right? Shift it one position and then we decrease the value of I, meaning now we go to the next. Okay, I go to the next. Right? So after we scan everything here, we need to insert the key into the right position. So we would have insert the key into AI plus 1. Okay. Why AI plus 1? Because when we reach here, it's smaller. We don't move, but we still decrease the I, right? So that's said, okay, here is bigger, decrease it, it's bigger, decrease it. So we have to insert the 4 right at the 8th position, right? So yi is greater than 0, then and ai greater than the key, then we move and we decrease. But if it's not, then I already reduced, meaning I is here. So we have to add 1, so we can insert it at the 8th position here instead of the 2, right? So that's why we have I plus 1. Okay, so that is what we have for the algorithm. Again, you already learned about this algorithm before. So nothing new. So the next one is something new. Okay, we have the algorithm after we design it. So now, how do we know that this algorithm is correct? Okay, let me show you uh, what we what I asked you before. Okay, is this algorithm always correct? Okay. Will it always terminate? And whether or not it's a good algorithm, how fast it is, how many memory it requires. All right. So those questions we have to answer them in this class. So starting with always correct. How do we know that this algorithm is correct? Remember that this algorithm can have infinitely many different inputs, right? And then every time when we give it an input, let's say a 1 billion. 1 billion elements, how do we know that the algorithm will produce a correct answer? We can say that, okay, I will test the program by running it for some input, right? And compare the result with what I expect. Uh, of course, with 1 billion is not easy to calculate, okay, by hand, of course. So even if we run it million times, it does not mean that it's always correct, okay? Because as I said before, there are infinitely many inputs we can give to this program. One element, two elements, 1 million, 1 billion, 1 trillion, whatever number we want, right? So always correct, we need to find a way to show that this algorithm is always correct. The second question is easier. Is this algorithm always terminate? Okay. We can see here that when we look at the program, the for loop will go from 2 to the n, where n is the number of elements in the input, right? So that said, it will repeat this for loop for n minus 1 times, right? So here, it goes from 2 to the 6. So it will finish working, yeah? Whatever we give for the n, it will finish working. And now, this step will do one time, right? For the while loop, this one means that we will scan the sorted part. Yeah. If we don't have this condition, then if we remove this, then the program may not terminate, right? Because when I is decreased, it can go beyond. And the program actually will crash, right? Because we decrease and then decrease, no element here, no element here, right? It may work for some time, but eventually it will go out of bound for the memory and the program may crash, right? So with this condition, it means that it will only scan the elements we have for the sorted part, right? And then this condition, true or false, so that said, the while loop will be executed, okay, at least here 2 times, right? So here 3 times. So that said, the program will terminate whatever input we give. That is easy, right? termination is easy to analyze, but the correctness is not easy at all. We have to show that this algorithm always correct, regardless of whatever input or whatever size of the input we have. So we need to have something in order to show that the algorithm is correct. And if you remember about discrete math, so when you learn about discrete math, obviously you should learn about induction, right? So we will try to use induction to show that this algorithm is always correct. Okay? So the correctness, in order to show that this algorithm is always correct, we will show that the algorithm is correct for a base case. Okay? So a base case, in this situation, I will pick that n is 1 is the base case, meaning that we have to show that the algorithm is always correct when the input has one element. So the base case will this algorithm be correct when the array has only one element? For example, we have n is 1, it means that we have the array with only one element, a1. Will this algorithm provide the correct answer? If an array has one element, then in fact when it jumps to here, why the unsorted part is not empty? The unsorted part is already empty, right? Because it starts from 2. Here we don't have element 2. So that said, the algorithm will simply finish working without even entering the follow, right? So that said, we have the input here has only one element. So what is the output? Same thing, because the algorithm does nothing, right? So is this input array sorted? Yes, every array with one element is sorted, right? So that said, base case, the algorithm is correct. Yeah. Now, induction assumption. Meaning that we assume that the algorithm is correct for any input of size k. Whenever we have k elements, we assume that the algorithm will produce the correct answer, right? And now we have to prove that induction proof. We have to prove that it's also correct when we have k plus 1 element. Okay? This induction assumption, when k is the number of elements, that said, we assume that if we have a1, a2 to ak, then the algorithm will produce a1 prime, a2 prime, ak prime. That is sorted, right? You assume that the algorithm is correct for k elements for the input. It means if the input is here, the output will be a sorted list, right? So that is the induction assumption. Now we prove it will be true for k plus 1 element. We do it as follows. If we have A1, A2, AK plus 1 as the list of input numbers. Now, how will this algorithm work? It will follow this algorithm as follows. Okay? Why the unsorted path is not empty, meaning we start with this A1 as the sorted path, and then the rest is the unsorted path. And remember that what we will do is that we will start inserting A2 into this sorted path, and then insert A3 into this, right? Etc. until we insert AK. Okay? If we look at this one, then it's exactly applying the algorithm here for k elements, because we insert A2, A3 to AK. So in other words, after k elements, we will have A1 prime lesser than A2 prime, AK prime, right? And this one is the sorted part. And now we will insert AK plus 1 into this list, right? But if this one is sorted, then inserting this one will give us a sorted list as well. And we can see that is a new list. Okay, that's why I call a double prime 2, right? A double prime k and a double prime k plus 1. So in other words, by inserting the last element into a sorted list, we also have a sorted list.